episode 34 of the World of FPGA Podcast. When sending or receiving fast signals by an FPGA, we need an appropriate logic behind this. And also fast IOs are important. Welcome to the World of FPGA Podcast. I'm your host, David Kirchner, and I will lead you through the world of FPGA. And now, let's begin. So first, Happy New Year! So it's a little bit late, but it took long until I can do the next records for this podcast. In the last and long ago episode, we talked about general and generic FPGA IOs. And today I want to look a little bit more at things we can use for high-speed connections. And this is not about gigabit transceivers or stuff like that. Gigabit transceivers will be a topic in one of the next episodes as far as I planned it. But often we need a little bit higher speed if we want to bring our data out of the FPGA to some device, or we want to get data into our FPGA. Electrical, it is normally we are using differential I/O standards, for example LVDS. But sometimes it could also be possible that we have to use single-ended I/O standards. And on the one hand, there are special standards also at single-ended I/O standards to doing high speed, for example, HSTL, or in the long form, high-speed transceiver logic. And this is all often used, for example, when you are connecting a memory device to your FPGA. Most memory devices like DDR4, DDR5 chips are having single-ended IOs. And to keep it short, yes, it is possible that you do high speed over single-ended IO standard pins you have on your FPGA. But there are some tricks about high speed on normal IOs. The first one is use input or output registers. They are often used they're often placed near to the I/O pads on the FPGA, on the silicon. Well, the second trick is, if it is possible, use DDR registers. So you can feed this DDR register with 2 data bits at the same time, and the output speed is the double as you have inside in your FPGA. If you go a step forward, use input or output shift registers. Okay, they're often called SERDES, so serial deserializer, but they are kind of shift registers. And always use defined timing constraints. Especially when you're doing high speed, timing constraints are necessary to get the high speed routed inside the device and outside to the to your receiver or to your source. And I will have a short look especially to the shift registers or SERDES. In the Xilinx or AMD world, they are called iSERDES for the input shift registers or OSERDES for the output shift registers. So SERDES isn't so it's input deserializer or output serializer. And the idea behind to use this kind of part inside your FPGA is, well, especially for FPGAs from AMD, but also for other ones, every I/O pin here has its own, for example, 8-bit shift register. So you can feed this register with 8-bit at the same time, and the shift registers will throw the data out of the FPGA at a very much higher speed than you're using inside your FPGA. So if you have an 8-bit shift register and you are running it, for example, internally at 150 megahertz, then you can theoretically get 1.2 gigabit output data rate out of your FPGA to the device you want to feed with your data. That's inside the FPGA is slow. 150 megahertz is for standards 7 series FPGAs from AMD. It's easy to use. And but on the output side, 1.2 gigabit is quite fast. So maybe your I/O standard, if it is, for example, LVDS LVCMOS 1.8 volts, it could be possible that that the signal integrity will not be so good as you would expect. But understand the idea behind this. You can create a higher parallel data stream inside your FPGA, what is easy to handle for an FPGA because there are a lot of registers and connection lines and so on, but on a much lower speed. So your internal design doesn't have to run at 600 megahertz or on 1.2 gigahertz, what isn't quite impossible, what is quite impossible. So if you want to get data fast out of your FPGA, then use the shift registers on the output pads of your FPGA. That's my idea, to use standard IOs on your FPGA for high-speed connections. This was also a talk on the last FPGA conference I gave last year in Munich. And that brings me to an announcement that's funny because it's, again, the FPGA conference in Munich this year, in the end of June in 2026. I will also be a presenter at the FPGA conference at Tuesday morning. So it's the second talk, when I'm informed. Yeah, it should be the second talk on the day. And my topic will be communication in multi-FPGA systems. And that is about using XE buses or XE Lite buses across FPGAs if you had a spreaded design with two or more FPGAs. And I will also create an example for this idea with two FPGA boards and some wires in between, which are showing the connection between two FPGAs, and then have a demo with, I don't know, maybe some switches and LEDs and so on. Yeah, and the next FPGA talk is also will also come in the next weeks. It is sometimes not so easy if you're living at the opposite side of the world. So Glenn is in Australia, I'm here in Germany, and it's not always so easy to find a date and a time when we can talk. And the last times we have planned this recording for a podcast, well, one of us was always sick, or one of our childs was sick, or always obstacles in our way. But we are in connection, and we will come back with our FPGA talk in the next weeks. It should be possible. So that's all for today. Here is soon, maybe with Glenn, maybe in a single episode. And next time it will be going about gigabit transceivers. Further information can be found at world-of-fpga.com/WFP034. If you found this episode helpful, please rate it on Apple Podcasts and share it with your colleagues and friends. That's the end of today's podcast episode. Thank you for listening and for your attention. So I say goodbye, here next time, your David Kirchner.